I think we can get started with the last talk of the day by Cristopher Jarzynski, who received his PhD in 1994 from University of California, Berkeley. Afterwards, he was postdoctoral researcher at University of Washington and at Los Alamos National Laboratory. Since 2006, he's professor at University of Maryland's Department of Chemistry and Biochemistry. And his research is mainly devoted to the study of statistical mechanics and thermodynamics at the molecular level, with a particular focus on the foundations of non-equilibrium thermodynamics. He has intensively worked on topics that include the application of statistical mechanics to problems of biophysical interest. His talk today is entitled Features of Nanoscale Thermodynamics. Thank you very much, Chris.
Okay, thank you, Carlos, for the introduction. It's both a pleasure and an honor to be here. Of course, I wish we could be seeing each other in person in Granada itself, but here we are listening to one another over Zoom. So as mentioned, the title of my talk is Features of Nanoscale Thermodynamics, and the question that kind of underlies this talk is the following one: what do the laws of thermodynamics look like when applied to very small systems? Now, when we learn thermodynamics from textbooks or in classes, generally we're taught that it is an inherently macroscopic theory. It's supposed to apply to macroscopic systems like steam engines and whatnot. But over the last several decades, there's been a growing appreciation that actually very small systems, down to the level of individual molecules or molecular complexes, can often exhibit thermodynamic-like behavior. So for instance, biomolecules that we have in all of the cells of our bodies act like tiny machines. They consume chemical fuel, they produce motion or useful work. And so it becomes interesting to ask, how do the laws that were originally developed to describe steam engines, how and to what extent and in what form do those laws apply to very small systems like biomolecules? Now, this isn't a question that I'm going to be able to answer in any kind of full generality during one talk. Rather, I'm going to try to describe some of the progress that has been made over the past several decades in understanding how the second law in particular applies to very small systems. And in fact, even within that topic, I'm going to focus largely on relationships between work and free energy in systems driven away from equilibrium. In fact, many of the results that I'm going to be discussing today have analogs that could be expressed in terms of entropy production or phase space contraction. And these relate very closely to some of the fluctuation theorems that Giovanni Gallavotti was discussing in his talk earlier today. Okay, so with that in mind, when we start asking how thermodynamics might apply to very small systems, a number of new features emerge there at the nanoscale. And by this, I mean features that are either not present or typically not relevant in macroscopic thermodynamics. So let me briefly list some of those. The first of them is the prominence of fluctuations. When we're dealing with very, very small systems, the size of a single molecule, then the random motions that we ordinarily associate with thermal fluctuations, those random motions become relatively prominent. So if we are looking at the behavior of a single molecule, it's constantly jiggling around in a random fashion. As a result, if we carry out some experiment many times on that molecule, we may get different results each time we carry out the experiment. And I'll give examples of that in a moment. So in this sense, these fluctuations become very prominent in small systems in a way that typically in large systems, those fluctuations, which are of course always there, but typically for macroscopic systems, they're just not so prominent. So if we want to develop a thermodynamic theory of very small systems, that theory should tell us something about these fluctuations. And I'll describe some of the results that have been derived over the past few decades. A closely related topic are these so-called violations of the second law. And I always put the term violations in quotes. I'm not suggesting that the second law has been overthrown. But when we subject a very small system to a thermodynamic process, then we may observe occasionally a kind of behavior that we would never observe in a large system. And I'll give examples. And this behavior may seem like a violation of the second law of thermodynamics. So we've learned something quantitative about these so-called violations, both experimentally and theoretically over the past few decades. And I'll describe some of that progress. A third new feature relates to the so-called arrow of time. When we ordinarily, if we view a movie of a macroscopic system, let's say a macroscopic system that's being subjected to some non-equilibrium process, often it's very simple, very easy for us to determine whether we're viewing that movie in the correct direction or whether it's being run backward for us. So, if we see a movie of a broken egg that puts itself together again spontaneously, we know that we're seeing a movie that's being run backward. This is sometimes referred to as the so-called arrow of time. It turns out that for very small systems, again, due to these fluctuations, this arrow of time becomes somewhat blurred in the sense that it's not quite so easy to distinguish the forward direction of time from the reverse direction of time. And it turns out, moreover, that that our ability to distinguish these two can be distinguish the forward from the reverse can actually be quantified in a way that can be measured in experiments. And I'll discuss that as well. And a fourth feature, new feature of thermodynamics at the nanoscale, involves feedback control and information processing. And this really relates to the old so-called paradox of Maxwell's demon, which goes back more than 150 years. And in recent decades, we've learned some new things about this topic, and I'll briefly describe some of those. And a final topic, which I've highlighted in red here because I probably won't have time to discuss it, involves strong system environment coupling. So the idea here is that when we have a macroscopic system that's coupled to some thermal surroundings, ordinarily we assume that the interaction energy between the system and its surroundings is entirely negligible. When dealing with a very small system coupled to its thermal surroundings, like let's say a single molecule of RNA immersed in water, then this assumption of negligible interaction energy is usually just simply not valid. And this means that we really have to rethink the way that certain thermodynamic quantities, in particular the heat that's exchanged between a system and its surroundings, we must rethink how those quantities are defined at the microscopic level. Again, I probably won't have time to get into this topic, although I do have a few slides prepared just in case I do have time. So what I want to do now is really go back and consider these one by one and show you some of the progress that has been made over the past few decades in understanding these features. So let's start with the fluctuations. And here, let me compare a macroscopic thermodynamic process with a microscopic analog of that process. So in the macroscopic case, imagine that I take an ordinary rubber band, I attach one end to an immovable wall, the other end to an ideal spring, and then here I am at the far end of the spring, kind of stretching pulling to try to stretch the rubber band. This system is assumed to be immersed in a room full of air at ordinary temperature and pressure. That air is the thermal environment. And I'll let lambda denote the distance from the wall, which is fixed, to the far end of the spring. And I'll think of lambda as a work parameter. So this is some variable that I control directly, and I use that control to act on the system of interest. In particular, let me imagine that I subject the rubber band to the following irreversible process. I start in a state of thermal equilibrium at lambda equals A. I then stretch the rubber band by varying lambda from A to B to some greater value B. And here, imagine that I do this relatively rapidly, so the system goes away from equilibrium. In doing so, I perform a certain amount of work on the system. Let me let W denote the work. And at the end, let me imagine that I allow the system to come to a new state of equilibrium corresponding to lambda equals B. So I begin in one equilibrium state, start in another, end in another equilibrium state, and at intermediate times, I drive the system away from equilibrium and I perform some work on it. In this case, the second law, as we all know, predicts that the work that's performed must be greater than the free energy difference delta F between the initial and final equilibrium states of the system. Okay, let's now look at a microscopic analog of this situation. Here, I take a single polymer-like molecule. Let's say a single strand of RNA. I attach the two ends of the RNA to microscopic polystyrene beads, which are shown as red circles over here. And by the way, the scales here are completely off. In reality, these beads are enormous compared to this poor little strand of RNA that's coupled between them. But this is meant to be just a schematic diagram. So I've got this RNA attached to the two beads. I immerse this entire system in a bath of water, let's say at room temperature and pressure. I grab one of the beads with a micropipette, a tiny suction device, and then I grab the other bead using a laser trap, or so-called optical tweezers. So again, I have a system of interest That's the RNA strand with the two beads. I have a thermal environment, that's the surrounding water. And I have a work parameter, lambda, which in this case is the distance from the pipette, which is fixed, to the center of the laser trap. And I can control the position of this laser trap. So once again, I imagine that I start in equilibrium at lambda equals A. I stretch the RNA strand by varying lambda from A to B. I do a certain amount of work when carrying out that process, and I allow the system to relax to a new state of equilibrium at lambda equals B. If I now go back and do this experiment multiple times, in principle, infinitely many times, always stretching it at exactly the same rate, then even though I'm being very careful to do the same process on the system each time, the system itself is going to be fluctuating randomly. You know, it's a small molecule undergoing thermal motions. And due to these random fluctuations, the amount of work that I perform is going to be different from one realization of the process to next. So from one time I stretch it to the next, the work is going to be different. But the second law suggests that in this situation, the average work, averaged over many repetitions of this process, will be greater than the free energy difference delta F. So we state the second law as an average rather than as a prediction about a particular outcome, the particular outcome of one experiment. So what emerges from these kind of considerations is the following semi-quantitative picture, where in the classical case, we have one sharp value of W. This is the work we do when we stretch the rubber band. This is greater than or equal to the free energy difference delta F. In the microscopic case, we have some distribution of work values, which I denote by rho of W. So think of this as a histogram of all the work values that were performed over many repetitions of the process. And in this case, the second law says that the mean of this distribution should be greater than the free energy difference delta F. But now there can be substantial fluctuations around the mean. In fact, every once in a while, we might even observe a value of work that's less than the free energy difference delta F. And it's these events down in this far left tail that are sometimes referred to as these so-called violations of the second law. And I'm going to return to that later on in the talk. Okay, so this kind of picture, I think, was already appreciated more than a century ago by people like Maxwell and Boltzmann and Gibbs, who realized that thermodynamics ultimately is based in a statistical theory. But what's new is the realization over recent decades that these fluctuations actually satisfy some interesting predictions that are stronger than just this second law inequality. So let me discuss two of them. And these are sometimes called fluctuation theorems, fluctuation relations, non-equilibrium work relations. So the first one I'm going to discuss is the following, and this makes the following claim. Instead of looking at the mean value of the work, which is the natural quantity to look at, let's look at the mean value of this quantity e to the minus beta W. Beta here is the inverse temperature, which is 1 divided by Boltzmann's constant times the temperature. And temperature here refers to the temperature of the surrounding thermal environment. So in the example I was talking about, this would be the inverse temperature of the surrounding water. The system itself is driven away from equilibrium, so it may not even have a well-defined temperature. W, again, is the work that's done during one realization of this process, and the angular brackets are an average over infinitely many realizations, or equivalently an average over this distribution rho of W. And the claim is that this average is going to be equal to e to the minus beta delta F. And the claim is that this is true even if the system is driven substantially far from equilibrium during the process. So this is not a near equilibrium or linear response-like result, although it's certainly consistent with the predictions of linear response theory when the process is carried out close to equilibrium. And if you think about it, this places a rather strong constraint on this distribution of work values. It's telling us that whether we carry out the process slowly or rapidly, close to equilibrium, far from equilibrium, this particular average is going to depend only on the initial and final equilibrium states of the system, because they uniquely determine this free energy difference delta F. Let me now mention another prediction. This was derived by Gavin Crooks about 22 years ago. And this one pertains to a pair of processes, which I'll refer to as the forward process and the reverse process. In the example that I was discussing, the forward process is the stretching of the single molecule, and I'll use the term reverse process to denote the contraction of the single molecule. So imagine I do an experiment where I stretch the molecule, measure the amount of work that's done there. I contract it, measure the work, and so forth, and I repeat the process many, many times. The red histogram here, or red distribution, is the distribution of work values for the stretching process. The blue distribution here is rho r of minus w. So this is the distribution of work values that are recovered during the contraction process. And then the second law would then say that the work that's done during the forward process must be greater than the free energy difference delta F, and that delta F must be greater than the amount of work that's recovered during the contraction process. Or in other words, or one consequence of this is that on average, we're going to do more work to stretch the molecule than we get back when we allow it to contract. Again, this is just the second law of thermodynamics. So we get this kind of semi-quantitative figure that's depicted by these two distributions. And now what Crookes showed was that even if the system is being driven far from equilibrium, these two distributions satisfy this very strong symmetry relation. The ratio of rho F divided by rho R at any value of W along this axis is given by this very simple expression, e to the beta W minus delta F, where again, the beta, W, and delta F have the same meanings as in this prediction over here. And this is very closely related, or at least it's very similar in structure to the fluctuation theorem for phase space contraction that Giovanni mentioned earlier. So I'm going to focus on these two results, but I should mention that these are two out of a larger set, maybe half a dozen to a dozen results, depending on how you count, that have been derived over the years, going as far back as early work by two Soviet scientists, Bochkov and Kuzovlov, in the late 70s and early 80s. There was a burst of work in the 1990s by all of these authors and others listed over here, including Giovanni. A very beautiful paper relating some of these results to single molecule pulling experiments by Hummer and Szabo. In 2005, Udo Seifert showed that a lot of these results could be brought together under within one kind of theoretical framework, and that theoretical framework really has grown into something that's often referred to these days as stochastic thermodynamics. I'm not going to have time to go into all of these other results in detail, but I do want you to be aware that the two results I'm focusing on are just two out of a broader class of so-called fluctuation theorems and fluctuation relations. Okay, let me show you, everything I've been discussing so far has been theoretical. Let me show you the results of some experiments that were carried out about 15, 16 years ago to test Crookes's prediction. So these were experiments involving the stretching and contraction of a single strand of RNA, very similar to what I've been discussing. The figure on the left here shows the kind of raw data. This is the force versus extension for about half a dozen cycles of stretching and contraction. The orange portions of the curve correspond to stretching, the blue to contraction, and without going into the details of why these lines have the shapes that they do, one thing you'll notice is that on average, the area under one of the orange curves is greater than the area under any one of the blue curves. And this is just the second law of thermodynamics in action. It's showing us that the work that we do in stretching the molecule on average is going to be greater than the work we get back when we contract the molecule. So these experimentalists carried out, and this was carried out in the lab of Carlos Bustamante at UC Berkeley under the leaderships of Felix Retort. He was the main researcher on this. And the experimentalists carried out several hundred repetitions of these stretching and contraction cycles. And from these repetitions, they determined these distributions of work values that are shown over here. So there's actually two pairs of distributions. There's the purple pair of work distributions, which were carried out on the wild type molecule that was harvested from E. coli. And then there's the yellow distributions that you see over here that were carried out on a mutated version of this RNA molecule. And I should mention that these distributions that you see over here are just the experimental analogs of these schematic distributions that I had shown over here. All right, so in order to test Crookes's prediction, the experimentalists then looked in this region roughly from 155 to 160 where the two yellow curves overlapped. There's not a great amount of overlap, but there's a certain amount of overlap. And in that region, the inset here shows the natural log of the left side of this prediction as a function of W over KT. And Crookes's prediction says that these points should lie on a straight line whose slope is unity. Here, the best linear fit gave a slope of 1.06, and this was well within experimental errors because, as you can see, the statistics here were not that great. There was not a large amount of overlap. So this was one of the early experiments that gave some experimental evidence in favor of Crookes's prediction. And in the time since then, and in fact, even going back a little bit earlier than that, numerous experiments have been carried out testing these predictions as well as other related results. These have involved various experimental platforms like mechanical oscillators, trapped colloidal particles, protein, the unfolding of a giant protein molecule, a single electron box. Despite the name, this is not a quantum system. This is essentially a classical two-state system. Without going into the details of these experiments, let me just mention that to date, all of the experimental results are in agreement with the theoretical predictions. So I think it's fair to say that over the last 2 decades or so, there's been a reasonable body of experimental evidence suggesting that these results, as well as others like them, are in fact very valid and in fact have been demonstrated experimentally. Let me just briefly mention one experiment that was carried out 6 years ago by 2 teams of scientists in Beijing. And this involved a quantum version of this non-equilibrium work relation. This result theoretically was first published in 2003 by Shaul Mukamel, but actually it already appeared in 2 earlier results that were never published, one by Jorge Kurchan and the other one by Hal Tasaki. And these authors basically showed that if you define work in the proper way for a quantum system, then this result applies to quantum systems as well, at least if the system is decoupled from the thermal reservoir during the actual process. So in 2015, an experiment was done to test this prediction. This involved a single ion of ytterbium trapped in a harmonic ion trap. The system was prepared in equilibrium. Its energy was then measured. The trap was then moved at some finite rate from its initial location to its final location. The final energy was measurement, so this was measured. So this involved 2 different measurements of energy. And then in the work, in agreement with these theoretical papers, was defined as the difference between the initial and final measured values of energy. So for the harmonic oscillator, this is just going to be h bar omega times the net change in the experimentally measured quantum number, n final minus n initial. Again, for the details of the experiment, I refer you to this paper that was published in Nature Physics. But down at the bottom here, I'll show you 3 different distributions of work values that the experimentalists obtained from these experiments. This distribution corresponded to pulling the trap at the slowest speed. This is at some intermediate speed, and this is at the highest speed. And then in this particular setup, the free energy difference, delta F, is equal to 0. So the theoretical prediction is that e to the minus beta W should be equal to unity. And when they plugged in the numbers from the experiments, they found that indeed the average of e to the minus beta was equal to unity within experimental errors in all three of these cases. So this, along with another paper that was published around the same time, provide the first evidence in favor of quantum mechanical versions of these non-equilibrium work relations. And whatever you think about the theoretical prediction or its experimental validation, I think it's amazing that experimentalists these days are actually carrying out these kind of experiments where they're measuring the amount of work performed on a single ion in an ion trap. So this, again, this kind of experimental ability gives us more a reason to ask the question, how does thermodynamics apply to these very, very small systems, or does it apply to these very small systems? Okay, let me move on to discussing some implications of these theoretical predictions for the second law of thermodynamics. So this prediction over here, which is stated as an equality, it immediately implies 2 inequalities. So first, it applies that the mean value of W must be greater than or equal to the free energy difference delta F. And you get from here to here simply by applying Jensen's inequality. Jensen's inequality is a mathematical result that says the average of e to the x must be greater than or equal to e to the average of x, where x can be any real random variable. Okay, well, this is basically the second law of thermodynamics. So this shows that this result is consistent with the second law. In fact, in some sense, implies the second law. But one can actually get a stronger statement than this one. And to see that, let's focus on this far left tail in the work distribution over here. So this is the tail where we occasionally see values of work that are less than the free energy difference delta F. And again, these are referred to in the literature as violations of the second law, with violations always in quotes. And I'm going to zoom in on this tail. And so I'm zooming in, again, everything to the left of delta F is a so-called violation of the second law. And we can then ask the question, what's the probability that the second law is violated by at least an amount zeta? And what I mean by that is the following. For any positive value zeta, suppose I carry out the experiment once. What's the probability that the work that I see is going to be less than delta F minus zeta? So that's what I mean by this question. In other words, what's the area underneath this distribution up to this point, delta F minus zeta? And in literally just a few lines of algebra, one can show that this equality implies the following inequality, namely the work under this tail up to this point is less than or equal to e to the minus zeta over kt. In other words, the area underneath this tail decays exponentially or faster in this thermodynamically forbidden region. And again, this puts a very, very strong constraint on seeing any sort of sizable violation of the second law. So we might be able to see a violation of the second law by an amount equal to 2 kt or 3 kt, because e to the minus 2 and e to the minus 3 is not so large. But we have no hope whatsoever of seeing a violation of the second law by an amount 100 kt, even though 100 kt would be a very, very small violation on the macroscopic scale. E to the minus 100 is such a fantastically small number that for all practical purposes, it is equal to 0. So this gives a very, very strong constraint on seeing any sort of sizable violation of the second law. On the other hand, suppose we take zeta here and make zeta be just infinitesimally larger than 0, then this inequality simply tells us that the net probability of observing any sort of violation of the second law must be less than or unity. And this is kind of a trivial result. It's just telling us that this entire distribution cannot all be to the left of delta F. And in fact, we already knew that because the mean value of W must be greater than or equal to delta F. So this inequality, which puts such a strong constraint on observing sizable violations of the second law, puts essentially no constraint at all on observing any sort of violation of the second law. If we just ask what's the overall probability that we see the second law violated, according to this inequality, it might be any number less than 1. It could be 0.9, 0.99, and so forth. So that a few years ago, that motivated some experimentalists to try to actually cook up a thermodynamic process where most of the realizations lead to so-called violations of the second law. And let me show you the results of that experiment. This involved a single electron transistor. Again, despite the word single electron, this is effectively a classical two-state system. You can read about the details over here. Let me just show you the results. So what's plotted over here, it looks like two distributions. It isn't. This is one distribution of work values that happens to be bimodal. We've got one bump over here to the left of 0 and another one over here to the right of 0. In this case, the free energy difference, the relevant free energy difference is equal to 0. So all of the work values to the left of 0 are so-called violations of the second law. Everything to the right of 0 is consistent with the second law. And you can see by eye that there are more violations than there are realizations consistent with the second law. In fact, it works out to be a ratio of about 2 to 1. So this is an actual experiment where, when the experimentalists carried it out many, many times, about 2/3 of the time, they got a value of work less than delta F, which is again, a so-called violation of the second law. Of course, the average work, when you average over both of these, over the entire distribution, the mean was actually a positive number. It's given over here, which is consistent with this inequality over here. So I find this actually quite astonishing that you can actually, the experimenters can actually in their lab perform or cook up a particular thermodynamic process where if you perform it many times, most of the time you get a value of work that's opposite to what the second law would predict if this were a macroscopic experiment. All right, let me move on now to this question of the direction of the arrow of time, and I'd like to frame this in terms of a hypothetical guessing game. So suppose that I show you a movie of some microscopic process. So let's say you see a thermodynamic process where some parameter is being varied from A to B in the movie. So for instance, let's say you see a movie of a single molecule that's being stretched. Your task now is to determine whether you're actually viewing the events in the order in which they actually occurred. In other words, did I actually stretch the molecule? Or if you're seeing a movie run backwards, in other words, did I actually contract the molecule and I'm just running the movie backwards for you to try to trick you into think that I stretched the molecule. And for the sake of argument, let's assume that you have all of the microscopic information that you want about this process. In other words, you can see the motion of every single atom in this movie. Again, this is a thought experiment. You have full information about this, except for the one piece of information, whether the movie is being run in the forward direction or in the reverse direction. And given all of the data that you can see, what is your best guess as to which of these is true? So this can be analyzed quantitatively as an exercise in statistical inference. We have two hypotheses. One hypothesis is that the molecule was in fact stretched. So that's the forward hypothesis. The other hypothesis is that the molecule was contracted, and now I'm running the movie backwards, so it just looks like it was being stretched. I'll refer to these as the forward, or F, and the reverse, or R hypothesis. And what can be shown, and I'm skipping the derivation, but what can be shown is that the one piece of information that allows you to make the best guess of which of these hypotheses is true is the work that was performed on the system. So once you take the information that you see in the movie about how every single atom is moving around, and you use that to calculate how much work was performed during the process that you see in the movie, no further information at all can help you to make the determination of which of these hypotheses is the correct one. In fact, once you've calculated the amount of work, the best guess that you have is given by this expression over here, namely the likelihood that the forward hypothesis was carried out, given the amount of work that you see in this movie that's been shown to you, is given by this very simple, in fact, universal expression, which is shown on the right over here. And we all know what this function looks like. It's a logistic function. So this is telling us that when the work is much greater than the free energy difference delta F, so when we're somewhere over here, then the likelihood that the forward hypothesis is correct is very close to unity. In other words, when the work is much greater than the free energy difference, then more likely than not, we're seeing the movie in the correct direction. On the other hand, when the work is much less than delta F, in other words, when the movie depicts a large violation of the second law, then with all likelihood, we're seeing the molecule being contracted. The reverse hypothesis is correct. So this is of course qualitatively in agreement with what we would expect. If we see a violation of the second law, we're going to guess that the movie is being run backward. But really, this makes a very strong quantitative prediction about the transition from the one behavior over here to the other behavior over here. This equation was first derived independently by Michael Schertz and colleagues, and then by Paul Maragakis and colleagues. This is in a slightly different context from the one I've been describing. This is in the context of numerical free energy estimation. This connection to the arrow of time and guessing the direction of the arrow of time was something that I discussed in this review article that I wrote about 10 years ago. And let me just briefly show you the results of an experiment that was carried out about 4 or 5 years ago, where this prediction was tested using a so-called quantum dot. Again, this is really just a classical two-state system. And again, without going into the details of the experiment, the various symbols that you see here, the circles, squares, and triangles, correspond to the experimental data. The red line corresponds to the theoretical prediction. In fact, there's no fitted parameters over here, and you can see that the experiment agrees very well with the theoretical prediction. So we're really kind of getting a quantitative handle on our ability to distinguish the direction of time's arrow. Okay, let me now finally move on to the final topic I want to discuss, which involves feedback control. And for this, let's start first at the macroscopic level. So the gadget that's or the cartoon that you see over here on the left involves a steam engine. And so as we know, what happens in a steam engine is steam from a boiler comes in here to the engine, and the engine then causes some wheel to rotate. And it turns out that it's very difficult to just naturally regulate the amount of steam that goes into a steam engine. So if we didn't have any sort of feedback process, this would be a highly erratic situation where sometimes the steam would come in at greater pressure, sometimes at lesser pressure. And so this wheel would turn in a very erratic fashion, sometimes faster, sometimes slower. And as you can imagine that, for various technological applications, or at least technological applications from 2 centuries ago, this would not be, this kind of erratic behavior would be very undesirable. So back in the late 1700s, a feedback device called a centrifugal governor, or metal sphere governor, was invented by James Watt and Matthew Boulton. And roughly this involves two spherical masses that are shown over here that are suspended in a way that they can rotate around a vertical shaft. And the idea is when this wheel is spinning, this shaft turns, these masses rotate around that shaft, and then the centrifugal force from that motion pulls the shaft up. And as the shaft goes up, that closes off a valve closes off a steam valve over here. So the idea is, if the motion of the wheel is too fast, the valve gets closed off more, and that reduces the amount of steam that goes in. Whereas if the motion is too slow, the balls drop because the centrifugal force is not that large, and that allows more steam in over here. And you can imagine that if you tinker around with this sufficiently, that then you can actually get this sort of gadget to be to regulate the speed of the wheel. And in fact, these centrifugal governors were a very important part of early steam engine technology. So all of that is a kind of long-winded introduction to say that what's depicted over here is autonomous feedback control. And by autonomous feedback control, I mean that the thing that's doing the feedback control is some physical gadget. So this is a gadget that was invented for that purposes, this metal sphere governor. I'm going to contrast this with what I'll call non-autonomous feedback control. And in non-autonomous feedback control, there isn't a gadget, there's just some unspecified external agent. Let's say, imagine this could be me. This agent is observing the motion of the wheel, and then based on its observations, it's either letting in a little bit more steam or cutting off the supply of steam in such a way as to try to regulate the output of this steam engine. So this external agent is trying to do the same thing that was accomplished by the metal sphere governor over here. And then the question is, given the powers of observation of this agent, what kind of control can the agent exert over this steam engine? I admit that this is a somewhat of an artificial distinction, but it's a useful one for exploring the kinds of questions that I'm going to be discussing now. Okay, so with this idea in mind, let's now imagine scaling feedback control down to the nanoscale. And this finally brings us to the Maxwell's demon thought experiment. This was described in a letter by Maxwell to his friend Peter Tate a little over 150 years ago. Maxwell imagined a container filled with gas. That container is divided by a partition into 2 halves. In the left half, we have a gas that is hot. In the right half, we have a gas that is cold. And Maxwell imagined this hypothetical creature, an external agent, or as we call it, Maxwell's demon, who stands nearby a small opening that can be closed off or opened. And then this this agent, whenever it sees an unusually fast particle moving from the right half towards the opening, it lets that particle through. And similarly, whenever it sees an unusually slow particle moving from left to right, it lets that particle through. And so we get an accumulation of fast particles on the left and an accumulation of slow particles on the right. Or as Maxwell put it, the hot system has got hotter and the cold colder, and yet no work has been done. Only the intelligence of a very observant and neat-fingered being has been employed. And I've underlined the words intelligence, the intelligence over here, to emphasize that in the way this thought experiment was originally formulated, this very much referred to non-autonomous feedback control. So Maxwell didn't have a gadget in mind, he just had some external agent in mind. And the point of this thought experiment, and the point Maxwell was making, is that an external agent with this kind of ability to perform feedback control at the level of thermal fluctuations, such an agent could bring about an apparent violation of the second law of thermodynamics. In this way, in this particular example, making a hot system hotter and a cold system colder without doing any work. This is sometimes referred to as a paradox, but logically there's no paradox over here. You know, Maxwell effectively introduced a magical creature into his thought experiment. So if you introduce some sort of magical creature like that, you shouldn't be surprised if laws of nature are going to be violated. Nevertheless, this is a very thought-provoking experiment, and it leads naturally to the question: is a mechanical Maxwell's demon possible? So, in principle, maybe not yet in practice because our technology isn't there, but in principle, could we create something analogous to the centrifugal governor, some kind of purely mechanical gadget or robot that would carry out the same sort of process that Maxwell's demon would carry out? And in that case, would this be a genuine violation of the second law? And this is an interesting experiment because, of course, or thought experiment, because, of course, at the macroscopic level, we certainly have feedback control systems, you know, robots and so forth that are capable of making measurements and acting on those measurements. You know, in principle, could we someday scale down to a really nanoscale robot that could do the same thing? So this really has some deep implications for the second law. This question has been posed, you know, more than a century ago. There was a very nice paper by Marian Smoluchowski back in 1912. There's also a very beautiful description of this sort of issue in the Feynman lectures, when Feynman talks about his ratchet and Paul device. Both Smoluchowski and Feynman answer this question in the negative. They say, no, a mechanical Maxwell demon is not possible, and they explain why they arrive at that conclusion. And they both argue that such a mechanical demon would indeed be a violation of the second law, but they say it's impossible. Starting in the early 60s and working through the early 80s, largely through the work of Rolf Landauer and Charles Bennett at IBM and Oliver Penrose in the United Kingdom, a somewhat more nuanced answer to this question arose. And that answer is kind of a yes, but. So roughly the idea that was proposed by Landauer and Penrose and Bennett is the following: that in principle, a gadget could be a gadget like Maxwell's demon could be invented, a purely physical gadget. But if this is a physical device and not some sort of hypothetical agent, if this is a physical device, then the information that it gathers about the motions of these molecules, that information must also be stored on some physical device. So they were arguing that such a gadget must effectively write information to some physical memory register. So that is depicted schematically over here. Imagine that we have some stream of bits that are all initialized in the 0 state. So think of this as an empty memory register. And this device, as it goes through its cycle, makes measurements, and the information from those measurements is written down into this stream of bits. So the ones and the zeros that you see over here reflect the random motions of the molecules that were observed by this gadget. And then, at least this is how the argument goes, the randomization of this stream of bits corresponds to entropy production. In fact, they argued that this randomization of bits should be interpreted on the same level as ordinary, thermodynamic entropy production, and the increase in the entropy of this memory register can compensate for the decrease in the entropy that's going on as this mechanical Maxwell's demon is carrying out its process. So in this sense, the answer to this question is yes, a mechanical Maxwell demon is possible, but only at the expense of writing information to some physical memory register. And this result brought about a very close relationship between information processing and the second law of thermodynamics. Okay, so with that background in mind, let me go back to this to the thought experiment that I'm almost done. I'm here on the second to the last slide. Let me go back to the to an experiment involving the stretching of a single molecule. Except now, imagine that we have some external agent who is making measurements on the motions of this bead, and then pulling the molecule either a little bit faster or a little bit slower, depending on how it sees this bead moving over here. And the goal of this agent is to stretch the molecule using as little work as possible. Let me let capital I denote the information that's gained by this measurement. This information can be quantified using standard tools of information theory. This was analyzed, this sort of class of processes was analyzed about 13 years ago by Takahiro Sagawa and Masahito Ueda. And they showed, using very, very general arguments, that in this situation, the second law should be replaced by the following inequality, namely that the average work must be greater than the free energy difference delta F minus KT times the average information that's measured by the external agent. So in other words, by making these measurements of these thermal motions, this agent can get away with doing less work to stretch the molecule than a naive application of the second law would imply. In fact, 2 years later, they were able to replace this inequality by this stronger equality that looks very much like a non-equilibrium work relation. The average of e to the minus beta w minus I is equal to e to the minus beta delta F. And then in the same year, an experiment was carried out where some of these predictions were in fact validated. So all of this really is similar in spirit to what Maxwell was arguing 150 years ago, namely that information about thermal beat the second law. But this goes a lot farther in making it very, very quantitative. And in fact, it's been validated now in experiments, not only this one, but other experiments that have been carried out later on. Okay, let me go to my summary slide. And if there's kind of one take-home message that I would like you to take from this talk is that the difference between thermodynamics on the macroscopic scale and on the microscopic scale, at least as pertains to the second law of thermodynamics, is that in the macroscopic case, we tend to have sharp values of quantities that we measure, whereas in the microscopic case, due to fluctuations, we'll have statistical distributions of those values. And as I've argued, if we account for these fluctuations properly, then the inequalities that we ordinarily associate with the second law, like the ones I've discussed over here, can be replaced by stronger equalities, like the two that I've focused on in this talk. And again, there are many others, or not at least a number of other equalities that are that have a form similar to this one that I haven't focused on. If you want to follow up on some of this, I can recommend, kind of shamelessly recommend, my own review article from about 10 years ago. At the same time, there was a very nice Reviews of Modern Physics colloquium by Campisi, Hangi, and Tauchner that focused on quantum aspects of this problem. And Takahiro Sagawa wrote a very nice review-like article on the information processing aspects of this problem. So with that, let me thank you for your attention, and I'll be happy to answer any questions.
Thank you very much, Chris, for such an illustrative talk. And yeah, well, now we have some time for questions. I see here that Alexander Hartmann has a comment. Yeah, I think, Alexander, maybe you can speak out. So, well, so let me, yeah, well, let's go first with Peter Solich and then with Alexander Hartmann.
Hi, Chris. Thank you very much. I had a question on the determination of the direction of time of the trajectory. if you had incomplete measurements, so for example, you had a finite time discretization or something, so that you couldn't get a precise estimate for the work, I'm assuming that in that case, additional information somehow would be useful. Is that something that you thought about or that can be quantified?
I assume you're right about that, but no, I haven't thought about that in any detail. Couldn't that be quantified? That's a good question. I suspect it could be. I haven't seen anybody think about that more carefully. So that could be a possible interesting avenue to explore. But unfortunately, I can't give you any answer here.
Okay, great, thanks.
So Alexander, feel free to make any comment if you wish.
Yes, hi, it's Alex. So I mean, when we look at the current slide, so first of all, thank you for a very extremely clear talk.
Thanks.
So when we have the availability of forward and backward experiments, then we can use Crookes' theorem to see whether we see this crossing point. And if we have data points there, then we know we have good statistics. But when you just use U relation, where we have the average of the exponential of minus beta the work, I just wanted to mention that one can plot the integrand of this. So e to the minus beta w times probability of w. And if this function has a clear peak, one is more or less sure that the statistics is good. But when the system gets larger or the process faster, often one misses the peak, and then one knows this estimate will not be good of the free energy.
Yes, that's a very good point, and it you know, this is in some sense it's a nice clean result, but on the other hand, it's a result that often is difficult to apply because having enough statistics to get the convergence of this average is often difficult. So if you're far from equilibrium, you would need prohibitively many realizations to get this average to converge. But as you've pointed out, there are certain statistical tests that you can implement to give you some confidence that you've got enough statistics. And the same is true over here. If you're very far from equilibrium, then the crossing point, then there's not going to be much statistics near this crossing point over here. So both of these have some issue with convergence.
Thank you.
Thanks for the comment.
Okay, then we have Omer Granek.
Hi, first,
Hello.
thank you very much for the very interesting talk.
Thanks.
Perhaps a slightly general question. What would you define as the present day core open problem in this relatively new field?
I don't know if I would have one problem, but certainly one where there's a lot of activity now is how do you extend these predictions to quantum systems, to open quantum systems. So the results that I discussed about quantum work relations, the results of Kurchan and Tasaki and so forth, those applied to closed quantum systems. How you even define quantities like work for an open quantum system is an area of very much activity, you know, a lot of activity these days. And so I personally would like to see that question answered. To what extent do these results carry over to open quantum systems?
Great, thank you.
Thanks for your question.
Okay, we have another question from BD.
Hi. Hi, Chris. It's Bertrand Duplantier speaking.
Hi, Bertrand.
Thank you for the talk. Thank you very much. Regarding the slides just before the last one, where you have the information content appearing, how does it relate, the relationship from Sagawa and Ueda with the Landauer's principle, the erasure? Does it appear somewhere there?
That's, I think, let's see, I know this is discussed in their paper. I think you can think of this as, no, actually, I think this is the opposite. So in some sense, the Sagawa and Ueda result is telling you how much you can benefit from gaining information, right? And Landauer's principle then tells you how much you have to pay in order to erase that information. So I guess that maybe one way to answer this question is if you use Sagawa and Ueda as a result to describe how much extra work you can get out of the system by measuring information, and then you combine that with Landauer as a result that tells you how much work you're going to do to have to erase that information, then at the end of the day, when you combine those two results, you find that you're back to the second law. So I would, that's how I would think that they would be most naturally related to one another.
Okay, thank you. Thank you.
Okay, thanks for the question.
Okay, there are a couple of more questions from Peter Hangi and Giancarlo Francese. Let's start with Peter.
Hi, Peter.
You have to unmute yourself, Peter, in order to speak. Now, I think, yeah, you can speak up now. Peter, are you there? No, we cannot hear you for some reason. Well, meanwhile, we can go with Giancarlo.
Hi, thank you for this very nice talk. I have quite general, so this is Giancarlo Francese speaking. I'm very general questions about how, can you give us examples in a biological system? Because of course, all these nice examples are made in labs to emphasize the effect, but we know that this must be relevant also in biological systems. So because they are the prototypical, nanoscopic system. So is there evidence and experiments that you can mention showing this, how relevant is this in biological processes?
So I would say the fluctuation relations that I've been discussing related to work and free energy, these really, I mean, the context for these is when you have some external agent that's carrying out some process. So it's hard to connect these very directly to biological processes, although it's easy to connect them to experiments that people have done on biological molecules, like single strands of RNA. There have been some results that apply fluctuation theorems or fluctuation relations. I think I've seen one to certain biological motors like the ATP synthase. So I have seen that applied to an ATP synthase that's not being externally manipulated; it's just being observed as a function of time. But I would say maybe the greater biological relevance is the fact that I think these fluctuation relations and other results that were derived around this time gave a lot of motivation for developing a formal and comprehensive thermodynamic framework for small systems. And I'd mentioned this briefly in passing. This is sometimes referred to as stochastic thermodynamics. And within that framework now, new results have been derived. For instance, over the past several years, these so-called thermodynamic uncertainty relations have been derived within that stochastic thermodynamics framework, and those results do seem to have some direct relevance to biophysical phenomena. Let's say the ones I've been discussing, just because this involves something that's deliberately carrying out some process, this is probably not as directly relevant to how biological machines operate.
Thank you very much.
Thanks.
Okay, maybe we can go with the last question by Jagua Moroti. Jagua, you have to unmute yourself in order to ask. Now.
It's a related to mitochondrial diseases, and some quantum phenomena described regarding electron transfer, particularly in the fourth complex.
Sorry, I'm not hearing the question.
Yeah, not sorry, but for some connection problem, or we cannot hear the question properly. Maybe you can chat, be synthetic, because we are running out of time. Well, I guess in that case, maybe you can always write an email.
Please
asking for more details. Well, thank you very much, Chris, again,
thank you
for such a nice talk, and thank you very much to all speakers of the day. Just let me remind you that tomorrow there are no talks. We will restart on Thursday at 4 p.m. with Julia Yeomans, and afterwards with Daniel Fisher. So see you on Thursday. Thank you very much again to all of you participants and speakers.
Goodbye, everybody.
Bye-bye.